The contents of Part 1 of Lesson 13 of Introduction to Cosmology can be summarized as follows. Setting up subscription, like, and notifications before watching, is a great help in video production. Dr. Hawking explained the concept of bug holes in his book, A Brief History of Time. According to Einstein's general theory of relativity, gravity manifests the curvature of space-time. Therefore, in places where gravity is strong, space-time is curved. If space-time is sufficiently curved, a wormhole can form, connecting two different spaces. A wormhole is a long, narrow passage connecting 2 points in space, just as a worm can pass through an apple and get to the other side faster than it can circle the surface. A worm's hole may allow it to travel across time and space. Wormholes are a concept that can only be explained through a combination of general relativity and quantum mechanics. According to general relativity, space-time is curved where gravity is strong. According to quantum mechanics, space and time are quantized. In other words, space-time is made up of small particles constantly clumping together. In black hole theory, the event horizon refers to the region surrounding the singularity at the center of a black hole. Crossing this region means reaching a point where not even light can escape from the black hole. The event horizon determines the size and shape of the black hole, varying based on its mass, charge, and angular momentum. The information paradox in black hole theory arises when applying both general relativity and quantum mechanics simultaneously. It revolves around the question of whether information about the matter consumed by a black hole is forever lost or preserved in some way. According to general relativity, a black hole, as per the no-hair theorem, carries no information except for its mass, charge, and angular momentum. Consequently, it should emit Hawking radiation unrelated to the initial state of the ingested matter, eventually evaporating. In this scenario, information about the consumed matter appears to be permanently lost. However, according to quantum mechanics, the state of a physical system is determined by a unitary operator, and since unitary operators have inverse operators, information must always be conserved. In other words, the current state of a physical system can be uniquely inferred from its past state and vice versa. In this case, the information about the material swallowed by a black hole must somehow be contained in the radiation emitted by the black hole. This paradoxical result between the two theories is known as the black hole information paradox. This paradox is one of the main topics in the field of black hole thermodynamics, and several solutions have been proposed. For example, attempts have been made to demonstrate that information is preserved through the holographic principle or the ADS-CFT correspondence. The theory of black holes is still an incomplete field, and more research and discoveries are needed. Let me explain the holographic principle and the ADS-CFT correspondence related to black hole thermodynamics. The holographic principle is the hypothesis that the information about the volume of space can be described as encoded on a light-like boundary, such as the gravitational horizon of a region. This principle originates from the Bekenstein-Hawking formula, which states that the entropy of a black hole is proportional to the area of its event horizon. This implies that the information about the matter swallowed by the black hole is encoded on the surface of the event horizon. The surface density of this information is limited by Planck units, referred to as Planck information or Planck bits. The ADS-CFT correspondence is the hypothesis that string theory formulated in an anti-de Sitter space, ADS, is equivalent to a conformal field theory, CFT, on the conformal boundary of the ADS space. This duality provides a non-perturbative formulation of string theory and represents the most successful implementation of the holographic principle. It is a significant advancement in string theory and quantum gravity theory. The utility of this duality lies primarily in the strong-weak duality. When the fields of the quantum field theory interact strongly, the fields of the gravitational theory interact weakly, making them mathematically more tractable. The holographic principle and the ADS-CFT correspondence play crucial roles in resolving the black hole information paradox and in constructing a quantum gravity theory. They also provide powerful tools for studying strongly coupled quantum field theories. The holographic principle and simulation hypothesis are related theories. The holographic principle suggests that information about the volume of space can be encoded on the boundary, such as the gravitational horizon of that space. Proposed to address the black hole information paradox, it implies that information about matter consumed by a black hole is encoded on the surface of its event horizon. The simulation hypothesis posits that our universe could be a simulation of some intelligent entity with the existence of minimum and maximum units in the universe. It is associated with the holographic principle, as both theories involve limits and phenomena reminiscent of quantum mechanics and computer operations. In other words, the holographic principle proposes that the universe is a 2D projection, while the simulation hypothesis argues that the universe is a simulation run by a computer. Both theories fall within the realms of physics and philosophy, presenting hypotheses that are challenging to scientifically validate or refute. Regarding the fate of an object falling into a black hole, the answer to whether it will undergo complete collapse is as follows. An object falling into a black hole does not undergo complete collapse. An object beyond the event horizon of a black hole is drawn towards its singularity due to the black hole's gravity. The singularity is a region where gravity becomes infinite and space-time is warped, violating known physical laws. Therefore, an object falling into a black hole will exist in some form at the singularity. Hawking radiation is the energy emitted from the singularity of a black hole. It arises due to quantum effects, and as the black hole's mass decreases, it emits this radiation. Hawking radiation is not emitted as a thin beam, but is composed of various particles, such as photons and neutrons. While there is a possibility that an object falling into a black hole could be expelled through Hawking radiation, it does not necessarily mean it will exist solely in the form of Hawking radiation. In more detail, an object falling into a black hole may exist in two possible forms at the singularity. Information form. The black hole does not violate the law of information conservation. Therefore, information about the object falling into a black hole should be preserved at the singularity. However, the nature of this preserved information in the region where known physical laws do not apply is yet unknown. Material form. The black hole emits energy through Hawking radiation as its mass decreases over time. Consequently, there is a possibility that material could be expelled from the singularity at the moment of the black hole's complete evaporation. However, whether this material retains the original form of the object falling into the black hole remains uncertain. In conclusion, the specific existence form of an object falling into a black hole has not been conclusively determined. It is anticipated that further research will provide more information on the nature of these objects through ongoing scientific exploration. An object that gets pulled into a black hole does not completely collapse Depending on its mass and angular momentum, part of the object may be emitted as Hawking radiation or remain in orbit around the black hole. The singularity of a black hole is a point where the uniformity of space-time breaks down, and if matter reaches the singularity, it would have infinite density and temperature. Therefore, if an object is fully absorbed into the singularity, its information would be completely lost. However, a black hole is not absolutely cold. It emits heat. This heat is known as Hawking radiation, and as the black hole's mass decreases, it emits more heat. Hence, part of the object pulled into the black hole could be emitted as Hawking radiation. Additionally, black holes possess angular momentum, which arises from the rotation of the object. The angular momentum of a black hole includes the angular momentum of the object, but the singularity itself does not have angular momentum. Thus, part of the object pulled into the black hole may remain in orbit around it. In conclusion, an object that gets pulled into a black hole does not completely collapse. Depending on its mass and angular momentum, part of the object may be emitted as Hawking radiation or remain in orbit around the black hole. An object that gets pulled into a black hole does not completely collapse and get ejected as a thin stream like Hawking radiation. Instead, the object is gradually compressed by the immense gravitational forces of the black hole. During this process, the object's energy is converted into heat and kinetic energy, which is then emitted by the black hole as Hawking radiation. This radiation causes the black hole's mass to gradually decrease. If the black hole's mass becomes sufficiently small, it could completely evaporate due to Hawking radiation. However, the object that is pulled into the black hole does not collapse completely and get expelled as a thin stream of Hawking radiation. The information about the object is stored within the black hole, and the energy emitted as Hawking radiation does not contain this information. In other words, the object that is pulled into the black hole does not completely disappear. It remains stored within the black hole. The exact nature of how the object exists inside the black hole is still uncertain. Some scientists believe that a singularity exists within the black hole, and that the object is absorbed into this singularity. Other scientists argue that there is no singularity, and that the object spreads out into the internal space of the black hole. This issue remains one of the unresolved puzzles in physics. Following the scent of a traveling wormhole, I glimpsed the door to the future, the smile of the multiverse, the dance of quanta, a symphony of time in the universe of information. Pathways of space-time, oh divergent roads, guard the future of multiple universes. Dreams of old mysteries once heard, whispers of time trapped in wormholes. The quantum dream of an information multiverse, a fragrance journeying backward through time. Past's future, future's past, a cyclical time, an endless exploration. The rapture of the multiverse, the realm of quanta, a transcended world, a connected silence. Pathways of space-time, oh divergent roads, unknown futures, myriad possibilities, parallel tales, the song of quanta, moments of wormholes, wings of light, the symphony of quanta in the multiverse of information.